Welcome guys, today we're going to be solving a very interesting modular congruence. We have to find all n in the positive integers such that 2 to the power of 2n plus 1 is divisible by 5. In other words, congruent to 0 modulo 5. So it doesn't seem like there's a good analytical way to solve this because we have a variable in the exponent and dealing with that, especially in congruences, may be pretty difficult. So honestly, let's just resort to making a table. Let's make a table for all n for the first few values and see if they are divisible by 5. And maybe we can then spot a pattern. So let's draw out this table here. We have for the first few values of n, then we're going to have n, and we're going to have for positive integers, so we'll start with 0, then 1, then 2, and so on. And this is going to be our result, f of n. So for 0, 2 to the power of 2 times 0 plus 1, that's just going to be 2 to the 0 plus 1. That's equal to 2. And 2 is not divisible by 5. Okay, well, let's keep going. Try 1. 2 to the power of 2 plus 1 equals 5. Okay, promising. We have for case 1, it is divisible by 5. But how will it be for case 2? We have 2 to the power of 2 times 2, which is 2 to the 4, plus 1. And that's equal to 16 plus 1, so 17. Also not divisible by 5. Okay, let's try 2 to the 2 times 3. It's going to be, seems like 2 to the 6 plus 1. That's going to be 64 plus 1, which is 65. Okay, again divisible by 5. I already see a small pattern coming out. We have every alternating digit. So for the odd ones, it seems to work. Well, maybe we can find a counterexample. We have 2 to the 8 plus 1. That's going to be 2 to the 8, 256, 257. Okay, doesn't seem, there definitely seems to be a clear pattern now. See for how the even n, the result always ends in 2 mod 5. And for odd n, it always results in 0 mod 5. Don't you see here it ends in 2, here in 7, here also in 7, all 2 mod 5, congruent to 2 mod 5. And for the odd ones, it's all 0, congruent to 0 mod 5. And if I take a guess for 2 to the 10 plus 1 for n equals 5, it should be divisible by 5 too. That's going to be 1024 plus 1. So yes, it is going to be 1025, which is divisible by 5. Okay, if we keep going, we find the exact same thing. Actually, but we can stop here, and we can now make a hypothesis, a conjecture. We're going to assume that n has to be odd for this to work. In other words, n has to be 2k plus 1, where k is some integer. But we don't know if that's always going to be true. There is a very neat way of proving it for all values that is called mathematical induction. So I'm going to move on. If we can prove this with mathematical induction, we successfully solved the inequality. If we don't, then things might get pretty hard. All right, so we made our hypothesis, our induction hypothesis, that n is going to be an odd number, or 2k plus 1, where k is some positive integer. So we have to start by assuming, we don't need a base case, by the way, because we already tested a few base cases, which work. Assume that 2 to the power of 2 times our n, which we said is 2k plus 1, plus 1 is equal to, well, it's congruent to 0 mod 5, then it's equal to 5 times some m, where m is some integer. Okay, and that simplifies to 2 to the power of 4k plus 2 plus 1 is equal to 5 times an integer. Okay, and we have to show that to do our induction, that this expression is satisfied for a case of k plus 1. So we have to show that 2 to the power of 4 times k plus 1 plus 2 plus 1 is equal to 5m. Or simplified again, it's 2 to the 4k plus 4 plus 6, plus 2, which is equal to 6. Plus 1 equal to 5m. All right, we have to show that, and we're going to be using our assumption. So let's go on with our assumption and just multiply our assumption by 2 to the power of 4, because then we get what we have to show. If you're not following, look at this. 2 to the 4k plus 2 times 2 to the power of 4 is equal to 5m minus 1 times 2 to the power of 4. Right? We took our assumption. Because this assumption is true, I moved over 1 to this side, and I multiply everything by 2 to the 4 in order to get what we have to show. 2 to the 4k plus 2 times 2 to the power of 4, that's just going to add 4 over to our exponent, which will make it 4k plus 6. All right, this is going to equal 2 to the 4k plus 6, as said. But what concerns us most is the right-hand side. We're going to have 16 times 5m, so 80m minus 16. Okay, and remember what we're trying to show, that 2 to the 4k plus 6 plus 1 is equal to 5 times some integer. And look at this. Final step here is to add 1. 2 to the 4k plus 6 plus 1 is equal to 80m minus 15. We added 1 to both sides. And what do you notice about the right-hand side now? Of course, it's divisible by 5. And we are basically done. We have shown that 2 to the 4k plus 6 plus 1 is equal to 5 times 16m minus 3. And from then, doesn't matter, it's 5 times some integer. M is an integer under our conditions. Therefore, the inductive hypothesis is true. 2 to the 4k plus 1 is equal to 5 times some integer. And that makes our original hypothesis for n being 2k plus 1 true. Therefore, we have indeed shown that the solution to this modular congruence is going to be n when n is an odd number. And that is it. I'm going to write solution here. Solution is when n is an odd number. N is odd. Odd positive integer, technically. And yeah, remember this. Remember, it's not always bad to make a table of values to later spot some pattern, which we can later prove by methods such as induction. That is it. Thanks for watching.